Some things in the universe feel so extreme that your brain tries to reject them before you even understand them. TON 618 is one of those things. Not because it sounds frightening, but because it exists right at the edge of what nature seems willing to build. A black hole so massive that every familiar picture of gravity suddenly feels inadequate. As if you brought a flashlight to measure the depth of an ocean. Here is the paradox that makes it unsettling. The universe follows laws that look elegant and precise on paper. Yet it still produces objects that challenge our deepest intuition. We are taught that black holes are the final remnants of dead stars. That idea feels contained. Almost reasonable. But TON 618 forces a different question. It is no longer about how a star dies, but about how the universe allowed something like this to grow without breaking its own internal balance. This is not a rumor, and it is not a dramatic story invented for attention. TON 618 matters because it is grounded in observation. We detect it as an extraordinarily bright quasar, a beacon shining from the early universe. That brightness is not decoration. It is evidence. It is the signature of matter falling inward, heating to extreme temperatures, and releasing enormous amounts of energy in a process that only a supermassive black hole can drive. Its name sounds like a label on a filing system. Cold and technical. Yet behind that label is a problem large enough to unsettle our confidence in simple explanations. If TON 618 truly carries the mass that measurements suggest, then our usual story about how black holes grow is not merely incomplete, it is missing a crucial chapter. One that explains how something can become so enormous when the universe itself was still young. Still assembling galaxies. Still finding its structure. This is the mindset to carry forward. We are not here to mythologize a cosmic monster. We are here to understand it. To separate what can be supported by physics from what we assume because it sounds impressive. The same tools astronomers use, the same logic they debate, and the same uncomfortable honesty they accept will guide this journey. The closer we move toward the truth, the clearer it becomes that something does not fully add up. TON 618 is not just a number and not just a record. It is a stress test. A test of how far gravity can be pushed before our models begin to strain. A test of how quickly the universe can construct extremes. A test of whether the laws we trust are complete, or simply accurate within the narrow corner of reality we have been able to measure so far. Before we talk about accretion disks, redshift, or mass estimates, hold on to one simple thought. If an object like TON 618 truly exists, then the universe has already shown it can go beyond what feels reasonable. That means the real boundary is not imagination. The real boundary is physics itself. And we are about to walk straight up to that boundary. If it is real, then where does the universe actually end? Before anything else, we need to be precise about what TON 618 actually is. It is not a glowing hole in space, and it is not a black object shining on its own. TON 618 is observed as an extremely luminous quasar, which means we are looking at the active core of a distant galaxy, where a supermassive black hole is feeding at an extraordinary rate. What our instruments detect is not the black hole itself, but the violent environment around it. Matter falling inward, heating up, and releasing enormous amounts of energy. This distinction is critical. A black hole by itself is dark and silent. It emits no light at all. If TON 618 were not actively feeding, it would be invisible to us. The reason it dominates our telescopes is the accretion disk, a swirling structure of gas and dust trapped by gravity, forced into rapid motion, and heated to extreme temperatures. As this material spirals inward, gravitational energy is converted into radiation, turning an otherwise hidden black hole into a quasar visible across the universe. Distance completely reshapes how we perceive TON 618. It is so far away that every photon reaching us began its journey billions of years ago. We are not observing it as it exists today. We are seeing it as it was in the deep past, when the universe was young and chaotic. To study TON 618 is to look back into a time when galaxies were still assembling, colliding, and growing at a pace that no longer exists in the modern universe. That period is often described as the quasar era. During this epoch, supermassive black holes were growing rapidly, fueled by abundant gas and frequent galaxy mergers. Quasars were not rare exceptions, but dominant engines shaping their surroundings. TON 618 belongs to this violent chapter of cosmic history, when gravity was building giants faster and more aggressively than our intuition would expect. There is, however, an important warning. When we speak about the mass of TON 618, we are not dealing with an exact measurement. The numbers come with large uncertainties, because they are inferred indirectly from light, motion, and models. Different methods can produce different values, yet even when those uncertainties are fully acknowledged, TON 618 still remains firmly in the category of the most massive black holes ever known. And this leads to a deeper question. All we see is a tiny point of light, a distant spark in the sky. Yet from that single point, we attempt to infer the presence of a black hole billions of times more massive than the Sun. How can such a small signal carry information about something so extreme and hidden? How does a point of light reveal what is happening in the darkest region at its core? When people say TON 618 is bigger than our solar system, they are not talking about a physical object with a surface or an edge you could point to. The key concept here is the event horizon. The event horizon is not a solid boundary. It is a limit written into space-time itself, a region beyond which escape is no longer possible. Light does not bounce off it. Matter does not crash into it like a wall. Crossing it simply means that every possible future path now points inward. To make this size meaningful, astronomers translate the mathematics into something our intuition can grasp. If the black hole at the heart of TON 618 were placed where our Sun sits today, calculations suggest that the radius of its event horizon would extend thousands of astronomical units outward. An astronomical unit is the average distance between Earth and the Sun. Even conservative estimates push this boundary far beyond the outer planets. Depending on assumptions about spin and mass, the event horizon could reach far past the orbit of Neptune and swallow Pluto so completely that it would no longer register as a meaningful landmark. This comparison reveals how misleading everyday images of black holes can be. Neptune and Pluto feel distant and extreme to us. Yet, on the scale of TON 618, they become minor reference points, like pebbles placed along an invisible line. The solar system that defines our cosmic neighborhood would fit entirely inside a region where space-time itself tilts inward with no possibility of return. It is crucial to understand that this size does not describe a giant black disk floating in space. The black hole is not a solid object filling that volume. The size refers only to the event horizon, a geometric boundary defined by gravity. Inside that boundary, the future is cut off from the rest of the universe. Outside it, escape is still possible. Nothing special marks the boundary visually. No glowing rim, no sharp edge, just a line written into the structure of space-time. This is what makes the scale so unsettling. The event horizon is only a boundary, but crossing it permanently severs all future communication with the outside universe. It is not destruction in the usual sense. It is disconnection, a single invisible threshold beyond which the concept of going back no longer exists. But if the event horizon emits no light and has no surface, how do we know it is that large at all? How can we measure the size of something that cannot be seen, touched, or directly observed? When discussing the mass of TON 618, one of the first things to understand is that there is no single universally agreed number. In the scientific literature, two broad ranges appear again and again. One places the mass at roughly 60 to 70 billion times the mass of the Sun. Another suggests a lower value, closer to 40 to 50 billion solar masses. This difference is not the result of sloppy science, but a reflection of how difficult it is to measure the mass of a quasar across billions of light years. The disagreement begins with the methods themselves. Astronomers do not measure the mass of a quasar directly. Instead, they infer it from light. Specifically, they analyze broad emission lines in the quasar spectrum, produced by fast-moving gas clouds orbiting the central black hole. Different studies use different spectral lines. Some rely on the hydrogen beta line, while others use carbon-4 or magnesium-2 lines. Each of these forms in slightly different regions around the black hole, under different physical conditions. This matters because those regions do not behave identically. Gas-producing hydrogen beta emission typically lies farther from the black hole, moving more slowly and often in more orderly orbits. Carbon-4 emission tends to come from gas closer in, where radiation pressure, winds, and outflows are stronger. If that gas is being pushed outward rather than purely orbiting, the line width no longer reflects gravity alone. The result is a mass estimate that can be systematically biased, often appearing larger or smaller depending on which assumptions are made. Orientation adds another layer of uncertainty. We do not know the exact angle at which we are viewing TON 618. If the system is viewed more face-on, the gas motions along our line of sight appear slower, leading to lower mass estimates. If it is viewed closer to edge-on, velocities appear higher and the inferred mass increases. Outflows and asymmetries in the line profile further complicate the picture, distorting the clean gravitational signal astronomers hope to isolate. Despite these complications, one conclusion remains stable. Even if we adopt the most conservative estimates, placing the mass near the lower end of the range, TON 618 is still among the most massive black holes ever identified. Objects in this category are extraordinarily rare. The debate is not about whether it is extreme, but about exactly how extreme it is. This uncertainty highlights a deeper truth. Measuring the mass of a quasar is nothing like weighing a physical object. It is an exercise in inference, statistics, and modeling, extracting hidden information from light that has traveled across most of the observable universe. So, how do these methods actually work in practice? How does astronomers turn spectral lines into a number measured in billions of solar masses? Top of form, bottom of form. The most powerful tool astronomers have for measuring the mass of a quasar is something called reverberation mapping. The idea sounds subtle, but it is built on a simple physical principle. The light from a quasar is not steady. The accretion disk around the black hole flickers and fluctuates as the inflow of matter changes. When the central region brightens or dims, the surrounding gas does not respond instantly. It reacts with a delay. Because light takes time to travel outward, surrounding the accretion disk is a region of fast-moving gas clouds known as the broadline region. These clouds absorb radiation from the central source and re-emit it as broad spectral lines. When the accretion disk suddenly becomes brighter, the gas clouds respond by brightening as well, but only after a measurable time delay. That delay is not random. It is simply the light travel time between the disk and the gas. By carefully monitoring how long this delay is, astronomers can measure the size of the broad line region. A delay of days, however weeks, or months corresponds directly to a physical distance measured in light days or light months. This gives a radius, not guessed, but measured from timing alone. No image is required. Time itself becomes the ruler. The second piece of information comes from the spectral lines themselves. These lines are broad because the gas is moving at extremely high speeds under the influence of the black hole's gravity. Due to the Doppler effect, gas moving toward us shifts the light one way, while gas moving away shifts it the other way. The wider the line, the faster the gas is moving. From this width, astronomers infer the typical orbital velocity of the gas clouds. Once both the radius and the velocity are known, gravity does the rest. Under the virial principle, which applies to systems bound by gravity, the mass of the central object is directly related to how fast material orbits at a given distance. Combine the size of the broadline region with the measured velocities, and the mass of the black hole emerges naturally from the equations. This is not speculation. It is classical gravitational physics applied on an enormous scale. Reverberation mapping is considered the gold standard because it relies on direct time measurements rather than assumptions alone. It has been applied to hundreds of active galaxies and forms the backbone for calibrating faster methods. Those faster methods, often called single epoch estimates, use one snapshot spectrum instead of years of monitoring. But they only work because reverberation mapping established the underlying relationships first. This raises the next challenge. Reverberation mapping can take months or even years of continuous observation. Something not always practical for extremely distant quasars like TON 618. So when astronomers cannot wait that long, how do they estimate the mass quickly from a single observation without losing reliability for extremely distant quasars like TON 618? Astronomers often rely on a faster technique known as single-epoch mass estimation. This method exists for a practical reason. Monitoring a quasar for months or years to perform full reverberation mapping is not always feasible. Instead, single-epoch methods attempt to extract the same physical information from a single spectrum taken at one moment in time. The foundation of this approach is an empirical relationship between the brightness of a quasar and the size of its broad-line region. Reverberation mapping has shown that more luminous quasars tend to have larger broad-line regions. Using this correlation, astronomers can estimate the radius of the emitting gas simply from how bright the quasar appears, without waiting to measure time delays. Once that estimated radius is combined with the velocity inferred from the width of a spectral line, the black hole mass follows through the same virial logic. The convenience is obvious, but it comes at a cost. Single epoch estimates carry much larger uncertainties than reverberation mapping. The errors are not small adjustments. They are often multiplicative. A mass estimate can be off by a factor of 2, 3, or even more. This does not mean the method is useless, but it does mean the result must be treated as an approximation rather than a precise measurement. Several physical effects contribute to these uncertainties. The geometry of the accretion disk and broad line region may not be spherical or uniform. If the gas is arranged in a flattened structure, the observed line width depends strongly on viewing angle. Winds and outflows driven by intense radiation can add non-gravitational motion, broadening or skewing spectral lines in ways that mimic higher or lower masses. Absorption along the line of sight can dim the quasar, leading to underestimates of the broad line region size. Because of these factors, different studies using single epoch methods can arrive at noticeably different mass values for the same object. This is exactly what happens with TON 618. Yet, despite these uncertainties, one conclusion is unavoidable. Regardless of which reasonable assumptions are chosen, the black hole is undeniably ultra-massive. What remains uncertain is not whether it is extreme, but how close it lies to the upper limits of what the universe can produce. If determining mass already involves such careful inference, the challenge only grows when we ask about distance and time. How do astronomers know how far away TON 618 truly is? And how do they translate that distance into a look back into the early universe? One of the most powerful ideas in modern cosmology is that observing distant objects is equivalent to looking back in time. This effect comes from redshift, the stretching of light caused by the expansion of the universe itself. As space expands, the wavelength of light traveling through it is stretched along the way. Shifting toward the red end of the spectrum, the farther the light travels, the more it is stretched, and the larger the redshift we observe for TON 618. The measured redshift is Z equals 2.219. This number encodes extraordinary information. It tells us that the universe has expanded by more than a factor of 3 since the light left this quasar. We are not seeing TON 618 as it exists now. We are seeing it as it was when the universe was only a few billion years old. During a phase of intense growth and violence in cosmic history, this is where confusion often arises. Distance in cosmology is not a single simple number. There is the light travel distance, which tells us how long the photons have been traveling. There is the co-moving distance, which accounts for how much the universe has expanded while the light was in transit. There is also angular diameter distance and luminosity distance, each useful for different calculations. These distances can differ by billions of light years for the same object, even though they all describe the same reality. The important point is not which number sounds largest, but what question each distance is answering. What matters physically is this. The light from TON 618 began its journey long before the Earth existed, before the Sun formed, before the solar system assembled. When those photons left the quasar, our planet was not even a possibility yet. The Milky Way itself was still evolving, and the universe looked profoundly different from the one we inhabit today. This changes how we should think about observation. We are not seeing TON 618 directly. We are seeing its memory. The image captured by our telescopes is a fossil record written in light, preserved across billions of years of cosmic expansion. The quasar may no longer shine this way in the present universe. It may already be quiet, dormant, or transformed, but its ancient light still reaches us, telling a story from a time we can never visit. And that raises a deeper puzzle. In this ancient memory, TON 618 shines with an almost absurd brightness, outshining entire galaxies. Why was the universe capable of producing objects so luminous in its youth? What physical process could power such extreme brilliance without tearing the system apart? The brightness of TON 618 pushes it into an extreme category known as hyperluminous quasars. Objects in this class do not merely outshine typical galaxies. Their luminosity can rival that of hundreds of trillions of suns combined. Even across billions of light years, they appear as dominant beacons in the cosmic darkness. This level of brightness is not just impressive. It is physically unsettling, because it demands an energy source far more efficient than anything familiar in everyday astrophysics. The key insight is that this light does not come from nuclear burning. Ordinary stars shine by fusing hydrogen into helium in their cores, converting a small fraction of mass into energy over millions or billions of years. Quasars operate on a completely different principle. Their power source is gravity itself. As matter falls toward the central black hole, it loses gravitational potential energy. That energy does not vanish. It is converted into heat, motion, and ultimately radiation before the matter crosses the event horizon. This process is astonishingly efficient. In stellar fusion, less than 1% of mass energy is converted into light. In black hole accretion, the efficiency can reach several tens of percent, depending on the spin of the black hole and the structure of the accretion disk. That means a small amount of matter falling inward can release more energy than an entire star over its lifetime. TON 618 is not burning fuel in the traditional sense. It is converting the deep structure of space-time into radiation. The accretion disk around the black hole acts like a vast energy processing system. Gas spirals inward at enormous speeds, heating up through friction, turbulence, and magnetic interactions, closer to the black hole. Orbital velocities approach significant fractions of light speed. temperatures rise to millions or even billions of degrees. Under these conditions, matter glows intensely across the electromagnetic spectrum. From infrared to visible light to X-rays, this radiation escapes outward, carrying away energy while the remaining matter continues its plunge. A useful way to imagine this is not as a fire, but as a cosmic power plant built at the edge of the event horizon. Gravity pulls matter in. Physics forces it to radiate before it disappears. The closer the matter gets to the black hole, the more efficiently energy is extracted. The black hole itself does not shine. The light comes from the last moments before matter is lost forever, when space-time is doing its most extreme work. This explains how TON 618 can shine so violently without exploding. The energy is not produced by an unstable core, but by a steady flow of matter converting gravitational energy into radiation. As long as fuel keeps falling in, the quasar keeps shining. When the fuel supply weakens, the light fades, leaving behind a dark but enormously massive remnant. Yet this description still hides a deeper question. What exact physical processes take in falling matter and turn it into such intense light? How does chaos near the event horizon organize itself into one of the most powerful energy engines the universe has ever built? At the heart of a quasar's power lies one of the most famous ideas in physics: E equals mc squared. Read as E equals mc squared. This equation tells us that mass and energy are not separate things, but two forms of the same reality. A small amount of mass contains an enormous amount of energy because it is multiplied by c squared, the speed of light squared. A number so large that it reshapes our intuition about what is possible in everyday life. We almost never see this conversion directly. Chemical reactions, like burning fuel, convert only a tiny fraction of mass into energy. Nuclear fusion inside stars is far more efficient, turning a small percentage of mass into light over long timescales. Even then, most of the mass remains locked inside the star. Black hole accretion pushes this process closer to its theoretical extreme. It does not require converting all the mass into energy. It only needs to convert a small fraction. And that fraction alone is enough to power luminosities that dwarf entire galaxies. The reason this works is that infalling matter does not simply vanish as soon as it approaches the black hole. As gas spirals inward, it accelerates and heats up under intense gravity. Its gravitational potential energy is transformed into kinetic energy and then into heat and radiation. This radiation escapes outward before the matter crosses the event horizon. The energy release happens at the very edge of disappearance, not after it. In this sense, the light from a quasar is the last visible act of matter before it is lost forever. Once material passes the event horizon, it can no longer send signals outward. Whatever energy remains is trapped permanently. The universe allows one final transaction. Matter gives up a portion of its mass energy to light, and only then does it vanish from view. This is what makes the process so dramatic. The quasar shines not because matter survives, but because it does not. The radiation we observe is the final glow of mass surrendering part of its existence to energy. Moments before space-time cuts it off completely from the rest of the universe. It is light born from gravity's point of no return. Yet this raises a critical problem. If gravity pulls matter inward so efficiently, why does everything not simply fall straight in? Why does material form a disk and radiate, instead of plunging directly and silently into darkness? One of the hardest problems in black hole physics is not how matter falls in, but how it manages to fall in at all. Any material approaching a black hole almost always has angular momentum. It is already moving sideways as it falls inward, which causes it to orbit rather than plunge directly. As long as that angular momentum is conserved, the material should simply circle forever, never reaching the event horizon, for matter to spiral inward. It must get rid of angular momentum. This is not optional. It is a strict requirement of physics. The central challenge of accretion is therefore not gravity pulling material in, but finding a mechanism that allows angular momentum to be transported outward so mass can move inward. Without such a process, the accretion disk would stall, and the quasar would fade into darkness. Early ideas imagined simple friction, like rubbing layers of fluid, slowing each other down. But ordinary molecular friction is far too weak to explain the observed accretion rates. The disks around supermassive black holes are vast and thin. Their particles rarely collide directly. Something far more powerful must be stirring the flow and creating an effective kind of viscosity. That mechanism is turbulence, driven by magnetic fields. The key concept is magneto-rotational instability, often abbreviated as MRI. In an accretion disk, different layers rotate at different speeds. Inner regions orbit faster than outer ones. When even a weak magnetic field threads the disk, it links neighboring layers together. Faster inner material pulls on slower outer material through magnetic tension, while the outer material drags back. This interaction destabilizes the flow. Small disturbances grow rapidly, turning smooth rotation into violent turbulence. MRI acts like a natural cosmic mixer, constantly churning the disk. In this turbulent environment, angular momentum is efficiently transported outward along magnetic field lines and turbulent eddies. As angular momentum moves outward, matter is freed to drift inward toward the black hole. The result is a self-sustaining process. Magnetic turbulence allows angular momentum to escape. That inward motion releases gravitational energy. Part of that energy maintains the turbulence itself. The disk becomes a dynamic system where motion, magnetism, and gravity reinforce one another. This is why accretion disks can shine steadily for millions of years. The importance of this process cannot be overstated. Without MRI and related angular momentum transport mechanisms, matter would pile up in stable orbits and never reach the inner regions. The accretion disk would stop feeding the black hole. The quasar would shut off. The immense brightness of objects like TON 618 depends entirely on this invisible redistribution of angular momentum. Once this mechanism is in place, another question follows naturally. If matter flows inward through the disk, how do conditions change with distance from the black hole? What does the structure of the accretion disk actually look like as we move from the outer regions down toward the edge of the event horizon? The accretion disk around a quasar like TON 618 is not a single uniform structure. It is better understood as a layered system. with conditions changing dramatically as matter spirals inward. A useful way to picture it is as three broad thermal zones, each defined by temperature, our radiation, and proximity to the black hole. In the outer regions, the disk is relatively cool by quasar standards. Temperatures here are measured in thousands of degrees rather than millions. The gas still glows intensely, but its radiation is dominated by optical and infrared light. This region often contributes much of the visible brightness we associate with quasars. From afar, this cooler outer disk gives the system a deceptively calm appearance, even though it is already rotating at hundreds of kilometers per second. Moving inward, conditions shift sharply. The middle region of the disk is far hotter. Temperatures rise to tens or hundreds of thousands of degrees. At these energies, the disk emits strongly in the ultraviolet. This zone is where radiation pressure begins to matter. Light itself pushes back on the gas, driving winds and shaping the disk's structure. Instabilities become more pronounced, and the flow grows increasingly turbulent and uneven. Closest to the black hole lies the inner region, where the physics becomes extreme. Here, temperatures reach millions or even billions of degrees. The dominant emission shifts to X-rays. Matter races around the black hole at significant fractions of the speed of light. General relativity is no longer a small correction. It governs the motion, the timing, and even the paths of photons escaping the disk. This region sits just outside the event horizon. In the last stable orbits matter can occupy before plunging inward. It is important to understand that these regions do not form neat, smooth rings. The accretion disk is not a clean, flat surface. It is chaotic, clumpy, and violently dynamic. Magnetic fields twist and snap. Hotspots flare and fade. Turbulence ripples through the plasma like storms on a stellar surface, but amplified to cosmic proportions. The disk behaves less like a calm structure and more like a boiling sea of charged particles under relentless gravitational stress. This complexity matters because not all parts of the disk contribute equally to what we observe. Some regions dominate the light output, while others shape variability and spectral features. Understanding which parts of the disk control the luminosity is essential for interpreting what we see from Earth. So, which region truly sets the brightness of a quasar like TON 618? Is it the vast outer disk, the violent inner zone, or something in between that decides how bright the quasar appears to the universe? The most important region of an accretion disk is the innermost stable circular orbit, often called ISCO. This is the closest distance from a black hole where matter can still maintain a stable orbit. Outside this radius, gas can circle the black hole for long periods. Inside it, no stable orbits exist. Once matter crosses this boundary, its fate is sealed. It plunges inward rapidly and disappears beyond the event horizon. The location of the ISCO is not fixed. It depends critically on the spin of the black hole. For a non-rotating black hole, the ISCO lies relatively far out. But for a rapidly spinning black hole, space-time itself is dragged around by rotation. This frame-dragging effect allows stable orbits to exist much closer to the event horizon. The faster the spin, the closer the ISCO moves inward, This matters because efficiency peaks at the ISCO. The deeper matter falls into the gravitational well before losing its ability to orbit. The more gravitational energy it releases as radiation, a black hole with high spin can extract far more energy from infalling matter than a slow spinning one. In this sense, the ISCO acts like the final compression stage of a cosmic engine, where matter is squeezed for maximum energy output just before it is lost forever. At these inner radii, relativistic effects dominate everything. Light emitted from the disk is strongly affected by gravitational redshift, losing energy as it climbs out of the deep gravitational well. At the same time, relativistic beaming makes the side of the disk rotating toward us appear dramatically brighter than the side rotating away. Frame dragging twists spacetime itself, altering orbital paths and enhancing turbulence. Time flows differently here, slower relative to distant observers. This is not a region that can be understood with simple physics. Newtonian intuition fails completely. To model what happens near the ISC, scientists must use general relativistic magnetohydrodynamics, often abbreviated as GRMHD. These simulations combine Einstein's theory of gravity with plasma physics and magnetic turbulence, tracking matter and fields as they evolve in violently curved space-time. They require some of the most powerful supercomputers available. The reason all of this matters is simple. The brightness of quasars like TON 618 depends strongly on how close matter can orbit before falling in, and that distance is controlled by spin. If spin plays such a decisive role in efficiency and luminosity, then understanding TON 618 fully requires knowing how fast its black hole is rotating. So how do astronomers measure the spin of a black hole that cannot be seen directly? Buried inside a quasar, billions of light years away, spin is the most difficult property of a black hole to measure. Yet it is also one of the most influential. While mass tells us how strong gravity is, spin determines how efficiently that gravity can be converted into energy. A rapidly spinning black hole pulls the innermost stable circular orbit closer to the event horizon, increasing accretion efficiency and boosting luminosity. Spin also strongly affects whether the system can launch powerful relativistic jets. Unlike mass, spin is not set once and for all. It reflects the entire growth history of the black hole. If a black hole grows mainly by accreting matter from a disk that always rotates in the same direction, its spin will gradually increase, potentially approaching the maximum allowed by general relativity. In contrast, if growth occurs through many short accretion episodes with random orientations, those angular momenta partially cancel, leading to a lower overall spin. Galaxy mergers add another layer of complexity. When two black holes merge, the final spin depends on their individual spins, their mass ratio, and the geometry of the merger. Some configurations spin the remnant up, others spin it down. Over cosmic time, a black hole like the one in TON 618 may have experienced both orderly accretion and violent mergers, leaving behind a spin that encodes this long and chaotic history. Observationally, spin is inferred indirectly, most often through X-ray spectroscopy. The key signal comes from ion emission lines produced in the inner accretion disk. These ion lines are naturally sharp at specific energies. but near a black hole they become dramatically broadened and distorted. Relativistic Doppler effects spread the line due to rapid orbital motion. Gravitational redshift stretches it further as photons climb out of the deep potential. Well, the closer the emitting gas lies to the black hole, the more extreme this distortion becomes. By modeling the shape of these broadened iron lines, astronomers can infer how close the disk extends toward the event horizon, and therefore estimate the location of the ISCO. Since the ISCO depends on spin, this provides one of the few observational handles on black hole rotation. However, this technique requires high-quality X-ray data and detailed modeling. Even for nearby systems, for an object as distant as TON 618, the challenge is far greater. The signal is faint, the uncertainty is large, and multiple physical effects can mimic each other. As a result, any spin estimate remains tentative. Yet, even without a precise measurement, spin cannot be ignored. It likely plays a central role in explaining the extreme brightness and possible jet activity of this quasar, which leads to the next question. If TON 618 produces jets, launching energy across vast cosmic distances, where does that energy actually come from? Is it extracted from the infalling matter? Or from the black hole itself? Astrophysical jets are among the most dramatic structures produced by black holes, and their existence points to two closely related but distinct energy engines. Both rely on magnetic fields, rotation, and extreme gravity. But they tap into different reservoirs of power. The first mechanism is known as the Blandford-Payne process, read as Blandford-Payne. In this picture, the energy source is the accretion disk itself. Magnetic field lines anchored in the rotating disk rise above its surface and bend outward. As the disk spins, these field lines act like rigid wires. Charged particles tied to them feel a centrifugal force that can fling material away from the disk along the field lines. The disk's rotational energy is gradually converted into a collimated outflow. In essence, the disk throws matter outward using magnetic tension as a lever. The second mechanism is even more extreme. It is called the Blandford-Znajek process, read as Blandford-Znajek. Here, the energy does not come primarily from the disk, but from the rotation of the black hole itself. A spinning black hole drags space-time around with it, an effect known as frame dragging. If strong magnetic field lines thread the region just outside the event horizon, the rotating space-time twists those fields. This twisting induces powerful electric currents and extracts rotational energy directly from the black hole. The result is a jet powered by the black hole's spin, not just by infalling matter. In both mechanisms, magnetic fields play the central role. They behave like tightly wound springs. As rotation twists them, energy is stored in the magnetic structure. When that energy is released, it accelerates plasma outward at relativistic speeds. The jet becomes narrow, focused, and extraordinarily stable over vast distances. In other galaxies, such jets have been observed stretching hundreds of thousands to even millions of light years, carving through intergalactic space, Jets are therefore not random byproducts. They are diagnostic tools. Their presence, strength, and structure encode information about the black hole's spin, the strength and geometry of its magnetic fields, and the surrounding environment. A powerful, collimated jet strongly suggests a rapidly spinning black hole threaded by ordered magnetic fields. A weak or absent jet may point to slower spin, chaotic fields, or an unfavorable disk geometry. This is why jets are often described as the fingerprints of a black hole system. They reveal the hidden properties that cannot be seen directly. In the case of a quasar as extreme as TON 618, any jet activity would signal a deep interaction between spin, magnetism, and accretion under the most extreme conditions the universe allows. Which leads to the next question. If a quasar can launch jets and radiation with such power, how does this energy affect the galaxy that hosts it? Does the black hole simply shine? Or does it actively reshape its entire environment? One of the most important ideas in modern astrophysics is AGN feedback. The process by which an active galactic nucleus both feeds on its surroundings and ultimately suppresses its own growth. A quasar like TON 618 is not a passive light source sitting quietly at the center of a galaxy. It actively reshapes the environment that sustains it. The first channel of feedback comes from radiation. The intense light emitted by the accretion disk ionizes the surrounding gas, stripping electrons from atoms and heating the medium to extreme temperatures. Hot gas does not cool easily. When gas cannot lose energy efficiently, it cannot collapse inward under gravity. The very radiation that signals rapid accretion also works to choke off the future supply of fuel. Radiation pressure adds another layer. Photons carry momentum. When a quasar shines with enough intensity, that momentum is transferred to the surrounding gas. The result is powerful quasar-driven winds. Outflows moving at thousands or even tens of thousands of kilometers per second. These winds can sweep gas out of the central regions of the galaxy, clearing out the material that would otherwise form stars or feed the black hole further. Jets contribute a more focused but equally dramatic form of feedback. As relativistic jets punch through the interstellar and circumgalactic medium, they inflate vast bubbles of hot plasma. These bubbles rise buoyantly through the galaxy and beyond, stirring and heating the surrounding gas. In galaxy clusters, similar processes prevent gas from cooling and forming stars, maintaining large reservoirs of hot, diffuse plasma for billions of years. The combined effect is self-regulation. As the black hole grows more luminous, it becomes more effective at disrupting its own fuel supply. Accretion slows, the quasar dims. Over time, the system settles into a quieter state. The black hole remains massive, but no longer actively feeding at a furious rate. The quasar phase is therefore temporary. Even for the most extreme objects. This feedback loop is crucial for understanding why galaxies do not grow without limit. Without it, gas would continue to collapse. Stars would form uncontrollably, and black holes could grow far beyond what we observe. AGN feedback provides the missing break, linking the growth of black holes to the evolution of their host galaxies in a tightly coupled way. Yet, this creates a profound puzzle. If quasars tend to shut themselves down, How did an object like TON 618 manage to grow so enormous so early in cosmic history? When the universe was young and time was short, how did it outrun its own self-limiting mechanisms? The existence of TON 618 confronts astronomers with a fundamental growth problem. To reach tens of billions of solar masses, a black hole must accumulate an enormous amount of material in a limited amount of cosmic time. The universe was only a few billion years old when the light we see from TON 618 was emitted. That leaves a narrow window for growth from an initial seed to one of the most massive black holes ever known. A central concept in this discussion is the Eddington limit. This limit describes a balance between gravity pulling matter inward and radiation pushing it outward. As a black hole accretes gas and becomes more luminous, the outward pressure from radiation increases. At a certain point, that pressure can counteract gravity, slowing or even halting further inflow. The Eddington limit therefore sets a maximum steady accretion rate under idealized conditions. It is crucial to understand what this limit does and does not mean. The Eddington limit is not a maximum mass. A black hole can grow arbitrarily large in principle. What the limit constrains is how fast it can grow through radiation-supported accretion. At the Eddington rate, a black hole's mass increases exponentially, but the characteristic timescale for doubling is fixed. Even under perfect conditions, growth takes time. This is where the tension arises. To reach the mass inferred for TON 618, the black hole would need to accrete near the Eddington rate for a very long period, with few interruptions. Yet, the early universe was chaotic. Galaxies were forming, merging, and rearranging themselves. Gas flows were violent and unstable. Maintaining steady, efficient feeding over such long timescales is far from guaranteed. Any prolonged pause in accretion slows growth dramatically. Miss a few critical episodes, and the final mass falls far short of what we observe. This makes the existence of ultramassive black holes at high redshift deeply puzzling. They seem to require not just favorable conditions, but an almost optimal growth history from very early times. This leads to a key question. If growth is limited by time and accretion rate, then the starting point matters enormously. How massive was the original black hole seed from which TON 618 grew? And what processes in the early universe could have produced seeds large enough to make this rapid growth possible? One proposed path toward building the first black holes begins with the very first generation of stars, known as population 3 stars. These primordial stars formed out of almost pure hydrogen and helium, with virtually no heavier elements. Without metals to cool the gas efficiently, these stars could grow far more massive than typical stars today, sometimes reaching hundreds of times the mass of the Sun. When such massive primordial stars reached the end of their lives, many would collapse directly into black holes. In the most common scenarios, this produces seed black holes with masses ranging from a few tens to a few hundred solar masses. These stellar seeds provide a natural and unavoidable starting point for black hole growth. Wherever the first stars formed, black hole remnants likely followed. The strength of this pathway is its simplicity. It relies on well-understood stellar physics and on processes that must have occurred in the early universe. There is no need to invoke exotic conditions. Population 3 stars almost certainly existed. and many of them would have left behind black hole remnants. The weakness becomes clear when we consider timescales. Starting from a seed of only a few hundred solar masses, reaching tens of billions of solar masses requires nearly continuous accretion at or near the Eddington limit for hundreds of millions of years. Any prolonged interruption slows growth too much. In a young universe filled with violent feedback, mergers, and gas depletion, maintaining such an ideal growth history is difficult. Some models suggest that early environments may have been more favorable than later ones. Dense gas reservoirs, frequent inflows, and lower metallicity could allow higher effective accretion rates, perhaps even exceeding the classical Eddington limit for short periods. These conditions might help stellar seeds grow faster than naive estimates suggest, but the margin remains tight. This leaves an uncomfortable question. If stellar seeds are too small to easily explain the most massive quasars at high redshift, is there another pathway? Could the universe create much larger black hole seeds directly? Skipping the slow climb from stellar mass altogether, a second pathway bypasses the slow climb from stellar mass entirely. It is known as the direct collapse scenario. In this picture, large clouds of primordial hydrogen and helium collapse almost directly into a black hole, without first fragmenting into normal stars. The result is an intermediate mass black hole formed in a single event, rather than the remnant of a star. The central challenge of direct collapse is fragmentation. Under normal conditions, a collapsing gas cloud breaks apart into many smaller clumps, each forming a star. To avoid this, the gas must remain hot and smooth as it contracts. That requires suppressing the cooling processes that would otherwise allow fragmentation to occur. This is where the cosmic environment becomes crucial. A strong ultraviolet background, produced by nearby star-forming regions, can dissociate molecular hydrogen. Molecular hydrogen is the most efficient coolant in primordial gas. If it is destroyed, the gas cannot cool effectively. Without cooling, pressure remains high. Fragmentation is suppressed, and the cloud can collapse as a single massive structure. Under these rare but physically plausible conditions, the collapsing cloud can form a massive object that rapidly becomes unstable and collapses into a black hole. The resulting seed can have a mass of tens of thousands to hundreds of thousands of solar masses. Compared to stellar seeds, this represents a leap of several orders of magnitude in starting mass. The advantage of this pathway is obvious. A much larger seed requires far less extreme accretion history to reach the masses observed in objects like TON 618. The growth problem becomes significantly easier. The drawback is rarity. The required conditions are stringent and may occur only in a small fraction of early halos. Even so, direct collapse seeds offer a compelling explanation for the earliest and most massive quasars. They provide a head start that could explain how black holes grew so large so quickly, even under the constraints of feedback and limited time. But a large seed alone is not enough. Even 100,000 solar mass black hole must still grow by orders of magnitude to reach the scale of TON 618. This raises the next question. Can accretion exceed the classical Eddington limit, allowing black holes to grow faster than normally expected? A third pathway pushes against what was once thought to be an absolute limit. This idea involves periods of super-Eddington accretion, episodes where a black hole grows faster than the classical Eddington rate would allow, rather than steady. Balanced feeding. These phases are chaotic, dense, and extremely luminous. The key lies in the structure of the accretion flow. At very high accretion rates, the disk can become geometrically thick rather than thin. In such disks, radiation has difficulty escaping. Photons produced by the hot, infalling gas become trapped within the flow and are dragged inward along with the matter. This effect, often called photon trapping, reduces the outward radiation pressure that would normally oppose accretion, because the radiation does not escape efficiently. It cannot fully push back against the inflowing gas. Gravity continues to dominate, allowing matter to fall in faster than the Eddington limit would predict. From the outside, the system may not even appear proportionally brighter, because much of the energy is swallowed along with the mass. What makes this scenario especially powerful is that it does not need to last forever. Even a few short super-Eddington episodes can dramatically alter a black hole's growth history. A brief period of runaway feeding early in cosmic time can set a black hole on a completely different trajectory, allowing it to reach enormous masses far sooner than steady accretion alone would permit. This idea has become one of the most active areas of research in black hole astrophysics. Numerical simulations are exploring how thick disks behave, how radiation and matter interact under extreme conditions, and how often such episodes might occur in the early universe. The physics is complex, and many uncertainties remain. But the potential impact is enormous. There is a sense of drama in this picture. A black hole does not need to feed calmly for billions of years. 1 or 2 brief eras of cosmic abundance may be enough. A single period of extreme overfeeding could be all it takes to turn a modest seed into a future giant. Yet accretion is not the only way black holes gain mass. This raises a final possibility. Can black holes grow suddenly through mergers, combining with others to become massive in a single event? Another pathway for black hole growth is merger-driven rather than accretion-driven. When galaxies collide and merge, their central black holes are brought together as well. Over time, these black holes can form a bound binary system and eventually coalesce into a single, more massive black hole. In principle, this allows mass to increase almost instantly, without the need for long periods of feeding. The final stages of such mergers release enormous amounts of energy in the form of gravitational waves. For a brief moment, the merging black holes become some of the most powerful emitters in the universe, radiating energy not as light, but as ripples in space-time itself. After the merger, the remnant black hole carries the combined mass, minus a small fraction lost to gravitational radiation. The appeal of mergers is obvious. Instead of slowly accumulating mass particle by particle, a black hole can gain a large fraction of its final mass in a single event. In a universe where galaxies frequently collided, especially at early times, mergers could provide a rapid path toward extreme masses. However, this route comes with its own obstacles. After 2 galaxies merge, their black holes do not immediately collide. They must first sink toward the center of the newly formed galaxy through a process known as dynamical friction. losing energy as they interact with stars and gas. As the separation shrinks, this process becomes less efficient. The system can stall at small distances, a challenge known as the final parsec problem. Solving this problem requires additional mechanisms, such as interactions with gas disks, triaxial galaxy potentials, or repeated minor mergers that keep the system evolving. While many solutions have been proposed, the details remain an active area of research. Mergers can speed up growth, but they are not guaranteed to proceed smoothly or quickly. In the early universe, galaxy mergers were more common than they are today. Structures were smaller, denser, and more likely to interact. This increases the likelihood that mergers contributed significantly to the growth of massive black holes like TON 618. Even so, mergers alone are unlikely to explain everything. They work best in combination with efficient accretion. This brings us to a curious limit. If mergers and accretion are both possible, why do we not observe black holes with masses of hundreds of billions or even trillions of solar masses? What sets the upper boundary? What prevents black holes from growing without bound? At first glance, nothing in the equations of general relativity forbids a black hole from growing to arbitrarily large mass. Gravity has no built-in cutoff. Yet when astronomers look at the universe, they do not find black holes with masses of 1 trillion suns. Objects like TON 618 already sit near the extreme edge of what we observe. This suggests that the universe imposes practical limits. Even if theory allows infinity, one limiting factor comes from fuel supply. A black hole can only grow as fast as matter is delivered to its vicinity. Galaxies contain finite amounts of gas. As black holes become more massive, they tend to live in environments where cold gas is depleted or heated. Feedback processes expel or stabilize the remaining gas, cutting off further growth. At some point, the surrounding galaxy simply cannot feed the central engine anymore. Another constraint arises from feedback efficiency itself. As mass increases, luminosity and jet power scale up. Extremely massive black holes are extraordinarily good at disrupting their environments. Radiation, winds, and jets heat gas on galactic and even cluster scales. This creates a self-limiting loop that becomes stronger with mass. The bigger the black hole, the more effectively it prevents itself from getting even bigger. There is also a cosmological factor. The universe is expanding and evolving. The era of frequent mergers, dense gas inflows, and rapid accretion does not last forever. As cosmic time progresses, structures grow larger and more isolated. Gas cools less efficiently. Merger rates drop. The window for runaway growth gradually closes. Black holes that fail to reach extreme mass early on are unlikely to do so later. Simulations suggest an additional subtle effect. At the highest masses, accretion disks may become unstable or inefficient at delivering material inward. Angular momentum transport, disk fragmentation, and radiation pressure all conspire to reduce the net inflow. Growth slows, not because gravity weakens, but because the machinery that feeds the black hole breaks down. Taken together, these effects point to a natural ceiling, not a sharp theoretical limit, but a statistical one. The universe allows monsters like TON 618 to form, but only rarely and only under near optimal conditions. Beyond that, growth becomes exponentially harder. This makes TON 618 especially important. It may sit close to the practical upper boundary of black hole mass that the universe can realistically assemble. If so, it is not just an extreme object, but a clue to the limits of cosmic structure formation, which raises the next question. If TON 618 is near the top of what is possible, what does its existence tell us about the early universe that made such extremes achievable at all? TON 618 belongs to a very small and controversial class of objects often described as ultramassive black holes. In this category, astronomers sometimes place candidates such as the black hole in the Phoenix, a cluster, and a handful of extremely distant quasars whose inferred masses push into the same extraordinary range. Each of these cases comes with debate, caveats, and large uncertainties. But together, they define a regime that is clearly different from the population of ordinary supermassive black holes. It is important to be precise about what largest means in this context. Rankings depend strongly on how mass is estimated, which spectral lines are used, how geometry is modeled, and what assumptions are made about orientation and accretion state. Small changes in method can reshuffle the order dramatically. As a result, claims about which black hole is the single largest should always be treated cautiously. What is not in doubt is rarity. Objects like TON 618 are vanishingly uncommon in the observable universe, among millions of galaxies and quasars surveyed. Only a tiny number approach these inferred masses. This rarity is not an observational accident. It reflects the fact that the physical conditions required to produce such extremes are themselves rare. The scarcity carries deep meaning. It suggests that ultramassive black holes do not arise simply by scaling up ordinary processes. They require a near perfect alignment of circumstances, early formation, abundant fuel, efficient accretion, favorable merger histories, limited disruption at critical stages. Miss any one of these, and growth stalls far below the ultramassive regime. In this sense, TON 618 is not just a large black hole. It is a statistical outlier, a product of a cosmic environment that briefly allowed everything to go right at once. When conditions align, the universe does not merely build bigger versions of familiar objects, it creates monsters. This leads naturally to the next question. Are those special conditions primarily local, tied to the properties of the host galaxy itself? Or do they arise on much larger scales, shaped by the structure of the cosmic web that feeds entire regions of the universe? On the largest scales, the universe is not random or uniform. Matter is arranged in a vast structure known as the cosmic web, composed of filaments, sheets, dense nodes, and enormous voids. Dark matter provides the skeleton of this web, and ordinary gas and galaxies trace its shape. This architecture determines where matter flows and where extreme objects are most likely to form. The nodes of the cosmic web are especially important. These are intersections where multiple filaments meet. Gas streams and galaxies are funneled into these regions by gravity. As a result, nodes become sites of intense activity. With high gas densities, frequent galaxy mergers, and rapid growth of massive structures. They are natural gathering points for fuel. Ultramassive quasars are most likely to arise in these environments. A black hole forming at the center of a galaxy located in a rich node has access to continuous inflows of gas along multiple filaments. These inflows act like invisible rivers, delivering fresh material over vast distances. Unlike isolated galaxies, which quickly exhaust or heat their gas, galaxies at cosmic intersections are constantly resupplied. In this picture, dark matter filaments function as highways. Gas flows along them, cooling and settling into galaxies as it goes. When conditions are right, this steady supply can sustain intense accretion for long periods, overcoming feedback and fueling rapid black hole growth. The cosmic web provides the infrastructure, the black hole merely exploits it. This larger context helps explain why objects like TON 618 are so rare. Only a small fraction of locations in the universe sit at the richest intersections of the web. Only a subset of those host galaxies with the right internal conditions. When both align, extreme growth becomes possible. The implication is profound. TON 618 may owe its existence not just to the properties of its black hole or its host galaxy, but to its position within the universe's largest scale structure. It is a product of cosmic geography, which raises the next challenge. If the quasar is so luminous, how can we learn anything about the galaxy that hosts it? What does the host galaxy of TON 618 actually look like when the quasar's light overwhelms everything around it? Observing the host galaxy of an extreme quasar like TON 618 is like trying to study a city while staring directly into a searchlight. The quasar's brilliance overwhelms the combined light of billions of stars, washing out the surrounding structure. In optical wavelengths, the host galaxy is often completely drowned, leaving only the point-like glare of the active nucleus. To get around this problem, astronomers turn to longer wavelengths. Infrared and submillimeter observations allow them to see past the glare. At these wavelengths, the quasar's direct emission is less dominant, while dust and cold gas in the host galaxy glow strongly. This shift in perspective reveals components that are invisible in optical light. Through these techniques, researchers search for telltale signatures. Hot dust heated by intense radiation re-emits energy in the infrared, molecular gas, traced by emission from carbon monoxide and other molecules, reveals the raw fuel for star formation. From these signals, astronomers estimate gas mass, star formation rates, and the overall scale of the host galaxy. The emerging picture, though still incomplete, points toward a massive host galaxy undergoing intense starburst activity. Such galaxies are forming stars at rates far higher than typical galaxies today. This fits naturally with the idea that rapid black hole growth and rapid galaxy growth occur together. Fed by the same gas inflows from the cosmic web, this coevolution is one of the central problems in galaxy formation. Observations across cosmic time reveal tight correlations between black hole mass and properties of the host galaxy, such as stellar mass and velocity dispersion. Objects like TON 618 represent extreme tests of these relationships. Do they follow the same rules? Or do they break them Even when the host galaxy cannot be imaged directly, it still leaves fingerprints in the quasar's light. Spectral features carry information about gas, dust, and motion in the surrounding system. This raises the next question. If direct imaging fails, what can spectroscopy alone tell us about the environment in which TON 618 resides? Spectroscopy is the primary tool that turns a distant point of light into a physical system we can analyze. Every emission line in a quasar spectrum acts like a fingerprint, revealing which elements are present and how they are behaving. Lines from hydrogen, carbon, oxygen, magnesium, and iron tell us not only what the gas is made of, but also how strongly it is being ionized by the central engine. The relative strengths of these lines carry even more information. Line ratios respond sensitively to gas density, temperature, and the intensity of the radiation field. By comparing observed ratios with physical models, astronomers can infer whether the gas is dense or diffuse, cool or extremely hot, and whether it is exposed to a gentle glow or a brutal flood of ionizing photons. In this way, a spectrum becomes a diagnostic map of conditions across regions we cannot resolve spatially. Line width adds a dynamic dimension. Broad emission lines indicate gas moving at thousands of kilometers per second. The deeper the gravitational potential, the faster the gas must move to remain bound. This is why line widths are used to estimate black hole mass. Gravity leaves its signature not as brightness, but as speed, encoded directly into the spread of wavelengths. Some quasars also show broad absorption lines, where chunks of the spectrum are eaten away rather than emitted. These features signal powerful outflows, winds of gas moving toward us at enormous velocities. They reveal matter being driven outward by radiation pressure and magnetic forces, carrying energy and momentum far from the black hole. Such winds are a direct manifestation of feedback in action, taken together. A quasar spectrum reads like a field report from an extreme environment. Composition, motion, energy, pressure, all of it is compressed into patterns of light. No single line tells the whole story, but each contributes a piece of the physical narrative. Yet, interpretation is not straightforward. Gas moving in orbit and gas being blown outward can both broaden and shift spectral lines. Winds can distort profiles that would otherwise trace gravity alone. This leads to a critical challenge. How do astronomers disentangle orderly orbital motion from violent outflows when both are written into the same spectral signatures? One of the most critical uncertainties in quasar mass estimates comes from a simple but profound question. Is the gas we are observing moving in orderly orbits around the black hole? Or is it being pushed outward by powerful winds? The answer determines whether the measured velocity truly reflects gravity or something else entirely. If gas motion is dominated by outflows, then its speed is no longer set purely by the black hole's gravitational pull. Radiation pressure and magnetic forces can accelerate gas to extreme velocities that mimic the signature of a much more massive black hole. In that case, using line width as a proxy for mass leads to systematic overestimates or underestimates, depending on the geometry and direction of the flow. Orientation complicates the picture further. A system viewed face on will show smaller line widths than the same system viewed edge on. even if the intrinsic velocities are identical. Without knowing the exact viewing angle, astronomers must rely on statistical corrections. These corrections work on average, but for extreme objects like TON 618. Small orientation biases can translate into large mass differences. Spectral line shape provides important clues. Outflows tend to produce asymmetric profiles, often with extended blue wings or overall blue shifts relative to the galaxy's systemic velocity. These features signal gas moving toward us at high speed. In contrast, gas dominated by orbital motion produces more symmetric line profiles centered on the expected wavelength. Careful analysis of these shapes helps distinguish gravity-driven motion from wind-driven motion. But the separation is rarely perfect. This is why the choice of spectral line matters so much. Hydrogen beta tends to trace gas farther from the black hole, where orbital motion is more dominant and outflows are weaker. Carbon-4 often forms closer in, where radiation pressure and winds are stronger. Using carbon-4 can therefore bias mass estimates if outflows are not properly accounted for. Different studies, using different lines, naturally arrive at different numbers. These effects lie at the heart of the spread in published mass estimates for TON 618. The disagreement does not reflect confusion about physics, but the difficulty of extracting a clean gravitational signal from a violently active environment. Each method captures part of the truth, but none sees the full picture on its own. This leads to an obvious next step. If individual spectral lines can mislead, is there an independent way to cross-check black hole mass using different observables or entirely different physical principles? One useful way to cross-check black hole mass estimates is through the concept of Eddington luminosity. This is the theoretical maximum luminosity a black hole can sustain if gravity and radiation pressure are in balance. For a given mass, there is a corresponding Eddington luminosity. Exceed it too strongly and radiation pressure should push infalling gas away, throttling further growth. This creates a powerful constraint. The observed luminosity of a quasar sets a lower bound on the black hole's mass. If TON 618 shines with an extreme luminosity, its mass cannot be arbitrarily small. Otherwise, the radiation would overwhelm gravity and blow away the surrounding fuel. The system would shut itself down almost immediately. The fact that it continues to shine implies a mass large enough to keep gravity in control. Astronomers often express this balance using the Eddington ratio. The observed luminosity divided by the Eddington luminosity. A ratio near 1 suggests accretion close to the theoretical limit. A much lower ratio implies more leisurely feeding. Ratios above 1 may indicate super Eddington phases or strong anisotropy in the radiation. For TON 618, plausible estimates place it in a regime of very high, but not obviously impossible. Eddington ratios. This approach does not replace reverberation mapping or spectral mass estimates. It lacks precision and depends on assumptions about geometry and radiation efficiency, but it serves as a sanity check. Any claimed mass must be consistent with the luminosity observed. If the numbers disagree wildly, something in the interpretation is wrong. In this sense, Eddington arguments act like guardrails. They do not tell us exactly how massive the black hole is, but they constrain how wrong we are allowed to be. They help narrow the range of acceptable solutions in a system where direct measurement is impossible. There is also a more dramatic implication. If TON 618 is radiating near its Eddington limit, it may be caught in a brief, unstable phase of rapid feeding, a moment when it is growing quickly, but has not yet triggered the full self-destructive power of feedback. A transient window, rare and short-lived, but visible across the universe. That raises a visceral question. If we could somehow approach this quasar, what would the environment around it actually do to us? How would radiation, winds, and gravity conspire to make the region around TON 618 lethally hostile to anything that dared come close, top of form, bottom of form? The region surrounding a quasar like TON 618 is not merely dangerous, it is effectively forbidden. Within a vast radius measured in light years, the environment becomes lethal to any familiar form of matter or technology. The primary reason is radiation. Intense ultraviolet and X-ray emission floods the surrounding space, ionizing atoms, stripping electrons, and breaking molecular bonds. In any biological analogy, this is radiation that would tear apart DNA faster than repair could ever occur. This radiation does not only destroy life as we know it, it is equally hostile to machines. High-energy photons penetrate materials, disrupt electronic circuits, flip bits, and damage semiconductors. Any probe attempting to operate in such an environment would be overwhelmed by noise, charge buildup, and radiation damage. The very tools designed to observe would fail long before reaching the inner regions. Closer in, the situation becomes even more extreme. The density of photons becomes so high that light itself begins to interact with light. When energetic photons collide, they can convert their energy into matter, producing pairs of electrons and positrons. This process, known as pair production, requires extraordinary conditions. But near a hyperluminous quasar, those conditions are naturally met. Space is no longer empty. It becomes a seething medium where radiation continuously transforms into particles and back again. A useful image is not of empty darkness, but of a dense ocean of light. A place where photons are so numerous that they collide, scatter, and transform. A region where radiation pressure, particle creation, and magnetic fields all coexist in a violently unstable balance. This is not merely bright, it is opaque in a fundamentally different way, dominated by processes that rarely occur elsewhere in the universe. This is why environments like this are considered natural laboratories for extreme physics. They push known theories to their limits. Quantum electrodynamics, plasma physics, and general relativity all operate simultaneously and at full strength. Conditions that can only be approximated in particle accelerators on Earth occur naturally and continuously near objects like TON 618. Yet, as extreme as these conditions are, they raise a deeper issue. In regions where gravity is strong and motion approaches the speed of light, perception itself becomes unreliable. Light is bent, time slows, paths twist, which leads to a fundamental question. When relativistic effects dominate what reaches our eyes and instruments, is what we see still an accurate picture of reality? Or only a distorted projection shaped by space-time itself, as matter in the inner accretion disk of TON 618 races around the black hole? It does not behave like a slow, symmetric system. Velocities approach significant fractions of the speed of light. And under these conditions, special relativity reshapes how light is emitted and received. One of the most striking consequences is relativistic beaming. On the side of the disk moving toward the observer, emitted light is compressed by the Doppler effect. Wavelengths shift toward the blue, and the intensity of the radiation increases. Photons are effectively packed closer together in time and direction. On the opposite side, where the disk is moving away, light is stretched toward the red and spread out. The emission appears dimmer and cooler. This effect goes beyond a simple color shift. Relativistic beaming concentrates radiation in the direction of motion. Light is not emitted evenly in all directions. It is focused forward, like the beam of a flashlight mounted on a relativistic race car. As a result, the approaching side of the disk can appear dramatically brighter than the receding side. Even if the underlying physical conditions are nearly identical, the visual outcome is profound. An accretion disk that is intrinsically fairly symmetric can look strongly lopsided. One half appears to blaze with intensity, while the other sinks into comparative darkness. The brightness contrast is not a sign of uneven heating, but of relativistic motion altering the flow of light itself. This is why classical models fail near black holes. Without special and general relativity, observations cannot be correctly interpreted. Spectral shapes, brightness distributions, and variability all depend on these effects. What telescopes record is not a simple image of matter in orbit, but a relativistically distorted projection shaped by velocity, gravity, and space-time curvature. The mental picture is almost surreal. One side of the disk seems to burn, the other to fade, even though both are made of the same plasma moving under the same forces. Reality is symmetric. Perception is not. And this distortion does not end with motion alone. Gravity itself bends light in extreme ways, which leads to the next phenomenon. Why do we sometimes see parts of the accretion disk that should be hidden behind the black hole? How does gravitational lensing allow us to glimpse the far side of the disk at all near a black hole like the one powering TON 618? Gravity does not simply pull on matter. It reshapes space-time itself. This curvature alters the paths of photons, bending light in ways that defy everyday intuition. What would be a straight line in ordinary space becomes a curved trajectory near a black hole. Because of this extreme curvature, light emitted from the far side of the accretion disk does not necessarily disappear behind the black hole. Instead, some of it is bent around and redirected toward the observer. The result is a distorted view in which we can see light from above and below, front and back, all at once. The geometry of space-time allows multiple images of the same region to reach us along different paths. One of the most important concepts here is the photon sphere. This is a region where gravity is strong enough that photons can orbit the black hole temporarily. These orbits are unstable, but they allow light to loop around the black hole one or more times before escaping. Photons that skim this region contribute disproportionately to what we see, piling up into a bright ring. This is why black hole images are not simply dark circles. They are surrounded by a luminous ring produced by strongly lensed light. The black hole's shadow is not the event horizon itself, but a silhouette defined by the capture and bending of photons. The glowing ring marks the boundary where light nearly escapes but almost falls in. Observations by the Event Horizon Telescope have confirmed this picture for nearer systems, such as the black holes at the center of the Milky Way and in the galaxy M87. While TON 618 is far too distant to image directly in this way, the same physics applies. The light we receive from it has been sculpted by the same gravitational lensing effects, encoded in its spectrum and variability. This bending of light adds another layer of illusion. We are not seeing a simple snapshot of matter in orbit. We are seeing a composite image assembled by curved space-time, mixing different regions and times into a single observation. Which brings us to the ultimate boundary. If light itself can orbit and barely escape, what happens when matter crosses the event horizon? What is the nature of the moment when escape becomes impossible? Crossing the event horizon of a black hole like the one at the heart of TON 618 is often imagined as a violent collision with an invisible wall. In reality, general relativity predicts nothing of the sort. For an observer falling freely, there is no sudden physical shock at the horizon itself. No alarm goes off. No barrier is felt. Locally, the laws of physics remain smooth and ordinary at that precise boundary. What changes is not what the infalling observer experiences, but what becomes possible at the event horizon. All future paths that once allowed escape disappear. Any signal sent outward, no matter how powerful, can no longer reach the outside universe. Light, radio waves, even gravitational signals are trapped. The horizon is not a place of destruction. It is a point of no return. From the perspective of a distant observer, the story looks very different. As matter approaches the event horizon, the light it emits is stretched by gravitational redshift. Signals take longer and longer to arrive. The infalling object appears to slow down, fade, and freeze near the horizon, never quite crossing it. This is not because it truly stops, but because space-time itself distorts the flow of time as seen from afar. Inside the horizon, the structure of space-time changes in a deeper way. The roles of space and time effectively switch. Moving inward is no longer a choice, but a necessity. Just as moving forward in time is unavoidable outside the black hole, the singularity is not a place one might reach. It is a moment in the future. All possible trajectories lead toward it. This is what makes the horizon so unsettling. There is no dramatic transition to mark it. No sound. No force. Just a silent loss of options. Beyond this boundary, the concept of turning back no longer exists. Not because of resistance, but because the geometry of space-time no longer allows it. There is no slamming door, no final warning. Only the quiet realization that every remaining second points inward. And this leads to an even stranger idea. If space and time trade roles inside the horizon, what does that actually mean for reality itself? How do we even describe a place where time behaves like a direction in space, and space behaves like time outside a black hole? Space and time behave in familiar ways. You can choose where to go in space. You can move left or right, forward or backward. Time, however, flows in only one direction, no matter what you do. The future arrives and the past remains inaccessible. This separation between choice in space and inevitability in time feels natural, almost invisible. In everyday life, inside the event horizon, that separation collapses. The geometry of space-time rearranges itself. The direction we call inward, toward the center of the black hole, takes on the role of time. It becomes a mandatory future. You cannot avoid moving inward any more than you can avoid tomorrow. Meanwhile, what we once thought of as time loses its usual meaning as a freely flowing parameter. This does not happen because a force suddenly grabs you and drags you toward the singularity. Gravity, in the usual sense, is no longer the right description. Instead, space-time itself dictates the allowed paths. The geometry of the region defines which directions exist and which do not. All possible world lines point inward, just as all world lines outside the black hole point forward in time. In this framework, the singularity is not simply a place at the center. It is more like a moment, a point in your personal future that cannot be delayed or avoided. You do not fall toward it in the ordinary sense. You progress toward it as inevitably as you progress toward the next second of your life. This is the point where Newtonian intuition completely fails. There is no analogy in everyday experience for a region where spatial direction becomes destiny. Language itself struggles to describe it, because our words evolved to match a universe where space and time remain separate. Yet, this abstract description raises a surprisingly human question. In a black hole as massive as the one powering TON 618, does this journey take longer? Would a falling observer experience more time before tidal forces become fatal, compared to falling into a smaller black hole? One counterintuitive aspect of black holes is how tidal forces scale with mass. Near the event horizon, tidal force is inversely proportional to the mass of the black hole. This means that the larger the black hole, the gentler the tidal gradient at the horizon itself. In a stellar mass black hole, the difference in gravity between your head and your feet becomes catastrophic well before you ever reach the horizon. In an ultramassive black hole, the same difference can be surprisingly small at first. For a black hole as enormous as the one associated with TON 618, an infalling observer could cross the event horizon without being torn apart immediately. Locally, gravity would feel almost uniform. There would be no dramatic stretching at that exact boundary. In this narrow sense, the horizon of a supermassive black hole can be described as smooth, even calm, compared to its smaller counterparts. This apparent safety is deeply misleading. The reason tidal forces are small at the horizon is not because gravity is weak, but because the gravitational field changes slowly over human-sized distances at that scale. As the fall continues inward, the situation changes rapidly. Space-time curvature increases steeply. The gradient in gravity grows sharper with every passing moment. Deeper inside, tidal forces rise dramatically. The difference in pull between different parts of the body becomes impossible to ignore. What was once gentle becomes violent. The same geometry that allowed a smooth crossing now ensures an unavoidable escalation toward destruction. The calm is only temporary. This creates a cruel rhythm. First, nothing seems wrong. Then, suddenly, everything is. There is no gradual warning that can be felt in advance. The transition from survivable to lethal happens over a short interval, driven by the accelerating curvature of space-time itself. The key lesson is this: a massive black hole does not make the journey safe. It only delays the inevitable. The horizon may feel forgiving, but it is merely the opening act. The deeper descent brings forces that no structure can survive, which leads to the final physical process. How exactly does this destruction unfold? How does spaghettification tear matter apart step by step as tidal forces grow without bound? Spaghettification is the vivid name given to the tidal destruction caused by extreme gravity near a black hole. The process begins because gravity does not pull equally on all parts of an object. The side closer to the black hole feels a stronger pull than the side farther away. This difference stretches the object along the direction of fall, while simultaneously compressing it sideways. Length increases. Width shrinks. At first, the effects are subtle. The stretching produces intense stress along the body. What would be perceived as pain is simply tissue being pulled beyond its elastic limits. As tidal forces grow, soft tissue fails, muscles tear, organs lose structural integrity. Bones, designed to withstand compression rather than extreme tension, begin to fracture. As the descent continues, the scale of destruction moves downward. Cells are torn apart as their membranes rupture. Molecular bonds break as electromagnetic forces are overwhelmed by gravitational gradients. Eventually, even atoms can no longer remain intact. Electron clouds are stripped from nuclei. Matter loses the structure that defines it at every familiar level. Throughout this process, the object is elongated into an ever thinner filament. The stretching does not stop because there is no stable configuration inside the horizon. Every moment brings a stronger gradient, a sharper difference in gravitational pull. What began as a recognizable form becomes an unrecognizable thread, aligned with the geometry of space-time itself. It is important to note that this description is still classical. It comes from general relativity applied to extended objects. As the scale shrinks toward atomic and subatomic dimensions, our certainty fades. At those extremes, quantum effects should matter. A full description would require a theory of quantum gravity, something physics does not yet possess. In that sense, spaghettification is both a prediction and a warning. General relativity tells us how destruction begins and accelerates, but it cannot reliably describe the final moments. The equations drive physical quantities toward infinity, signaling that the theory is being pushed beyond its domain of validity. The image is unsettling but precise. You are not crushed. You are not burned. You are drawn out, thread by thread, becoming a filament woven into the fabric of curved space-time, a strand in the loom of the universe. And that leads to the deepest problem of all. If general relativity predicts infinite density and infinite curvature at the singularity, does that mean the theory itself is breaking down there, or is the singularity a signpost pointing toward a deeper, unfinished layer of physics? In the mathematics of general relativity, the singularity is the point where familiar quantities lose their meaning. Density grows without bound. Space-time curvature diverges toward infinity. Equations that otherwise describe the universe with remarkable precision begin to return answers that are not just extreme, but undefined. This is not merely a prediction of something violent. It is a signal that the theory has reached the edge of its applicability. In physics, infinities are rarely accepted as literal features of reality. They usually indicate that a model is being pushed beyond the regime it was built to describe. General relativity treats spacetime as a smooth, continuous fabric. Quantum physics tells us that at sufficiently small scales, nature becomes discrete, probabilistic, and fluctuating. At a singularity, these two frameworks collide, and neither can fully describe what is happening on its own. This is why singularities are often interpreted not as real physical points, but as placeholders for unknown physics. They mark regions where a deeper theory must take over. A theory capable of unifying quantum mechanics and gravity, commonly referred to as quantum gravity. Such a framework would describe space-time not as infinitely divisible, but as something with an underlying microscopic structure. Several candidate approaches attempt to fill this gap. String theory proposes that the fundamental constituents of reality are not point particles, but tiny vibrating strings, whose different modes give rise to particles and forces. In some versions, singularities may be softened or resolved by extended structures and extra dimensions. Loop quantum gravity takes a different path, suggesting that spacetime itself is quantized, built from discrete loops or networks. In this picture, extreme compression could be halted by quantum geometry effects before infinities ever form. These ideas remain incomplete and untested in the regimes where singularities occur. No experiment can yet probe conditions anywhere near the interior of a black hole. As a result, the singularity remains a boundary rather than a destination, a place where our equations stop giving meaningful answers, and our confidence in prediction ends. This is what makes black holes so important. They are not just astrophysical objects. They are stress tests for our deepest theories. Ton 618. By pushing mass, energy, and curvature to extremes, forces us to confront exactly where our understanding runs out. Yet, even if we cannot cross the horizon or describe the singularity, there may still be ways to learn about the physics near these boundaries. Subtle signals encoded in light, motion, and space-time itself might carry indirect information from regions we can never enter. Which raises the next question: is there a way to probe the near-horizon environment of a black hole to study its extreme physics? Without ever falling into it, direct exploration of a black hole is impossible. But its environment leaves measurable traces that allow indirect probing of extreme gravity. One of the most powerful clues comes from variability. A region cannot change faster than light can crush across it. When the brightness of a quasar fluctuates on short timescales, those variations set an upper limit on the size of the emitting region. Rapid flickering implies a compact source, pointing directly to processes occurring close to the black hole. X-ray observations are especially valuable. In the inner accretion disk, hard X-rays produced by a hot corona illuminate the disk surface and are reflected back toward the observer. This reflected radiation carries imprints of strong gravity. Spectral features, especially ion emission lines, appear broadened and skewed by relativistic motion and gravitational redshift. The degree of distortion encodes information about how close the disk extends toward the ISCO and how extreme space-time curvature has become. Timing adds another layer of insight. X-ray reverberation lags occur when changes in the primary X-ray source are echoed moments later in the reflected emission from the disk. The delay corresponds to light travel time across the inner regions. By measuring these tiny lags, sometimes only seconds or minutes long in nearby systems, astronomers can reconstruct the geometry of the innermost accretion flow. Even for distant quasars, the same principles apply. Stretched over longer timescales, future measurements of polarization promise to go even further. The orientation and degree of polarization of X-rays depend on scattering geometry, magnetic field structure, and relativistic effects near the black hole. Polarization can reveal disk inclination, probe the structure of the corona, and test predictions of general relativity in the strong field regime. It adds directional information that spectra alone cannot provide. Together, these techniques show that proximity is not required for understanding. We do not need to see the singularity or cross the horizon to learn about extreme gravity. Light, timing, and polarization carry encoded messages from regions only a few gravitational radii from the black hole. By decoding those messages, physics reaches into places matter itself cannot return from. This leads naturally to the future. If indirect probes already reveal so much, what will the next generation of telescopes uncover? Which instruments will be able to read TON 618 with greater clarity in the coming decade? The challenge with objects like TON 618 is not a lack of light, but too much of it. The quasar outshines everything around it, masking the very galaxy that feeds it. This is where instruments like the James Webb Space Telescope change the game. Operating primarily in the infrared, JWST can peer through dust and reduce the dominance of the quasar's glare, revealing the underlying structure of the host galaxy with unprecedented sensitivity. In the infrared, dust heated by stars and by the quasar itself glows brightly. JWST can separate these components, allowing astronomers to estimate stellar mass, star formation rates, and the distribution of warm dust. This makes it possible to study whether the host galaxy of TON 618 is still actively forming stars, or whether quasar feedback has already begun to suppress that process. ALMA provides a complementary view. By observing at millimeter and submillimeter wavelengths, ALMA maps cold molecular gas, the raw fuel for star formation and black hole accretion, emission from molecules such as carbon monoxide traces, where gas is concentrated, how it is moving, and how much of it remains available. These measurements reveal whether the galaxy is being replenished or starved. Together, JWST and ALMA allow a powerful synthesis, Infrared data tell us what the stars and dust are doing. Sub-millimeter data tell us where the gas is and how it flows. Combined, they show whether the galaxy is in a starburst phase, rapidly converting gas into stars, or whether feedback from the quasar is heating, expelling, or stabilizing the gas and shutting growth down. This is crucial because black hole growth cannot be understood in isolation. The host galaxy is not just a backdrop. It is an active participant. Without knowing how much gas is present, how it moves, and how stars are forming, any story about the rise of an ultramassive black hole remains incomplete. There is a poetic symmetry here. We learn about the monster by studying the shadows it casts through its own dust and gas. The very material that feeds the black hole also hides it. And only by looking at the right wavelengths can we glimpse the full system at work. Yet space telescopes are only part of the picture. On Earth, a new generation of giant ground-based observatories is coming online. How will these instruments change what we can learn about objects as extreme and distant as TON 618? The next major leap in studying objects like TON 618 will come from extremely large ground-based telescopes, led by the Extremely Large Telescope, with a primary mirror tens of meters across. Its photon collecting power far exceeds that of current observatories. This matters enormously for distant quasars, where every detected photon carries information from the early universe. A larger mirror does more than gather more light. It enables spectroscopy at much higher resolution. Fine details in spectral line shapes that are currently blurred or lost in noise become measurable. Subtle asymmetries, shifts, and wings in emission lines can be mapped with precision. This directly reduces uncertainties in black hole mass estimates by better separating orbital motion from outflows and winds. High spatial resolution is just as important. Adaptive optics on extremely large telescopes can partially disentangle the light of the quasar from that of its host galaxy. Structures that were previously merged into a single glare can be separated. This makes it possible to study stellar populations, gas distributions, and feedback effects in the host galaxy at a level never before achievable for such distant systems. These instruments will also probe chemical composition in greater detail. Metallicity measurements reveal how many generations of stars have already lived and died in the host galaxy. They trace enrichment history and gas inflow pathways. Combined with kinematic data, this allows astronomers to test models of galaxy growth, merger history, and quasar-driven feedback with far fewer assumptions. The significance of this shift cannot be overstated. Many debates surrounding ultramassive black holes persist because the data are just barely sufficient. With extremely large telescopes, questions that were once framed as possibilities move into the realm of measurement. Hypotheses can be ruled out or confirmed with direct evidence rather than inference alone. In this sense, the Extremely Large Telescope represents a transition point. It does not merely refine existing observations, it changes what kinds of questions can be asked. For objects like TON 618, it promises to transform speculation into precision. Yet even photons have their limits. Light tells us about matter and radiation. But there is another messenger that does not care about dust, glare, or distance in the same way. Ripples in spacetime itself may carry information from the most extreme events. Which brings us to a completely different observational window. What can gravitational waves tell us about the growth and history of ultramassive black holes? The laser interferometer, space antenna, known as LISA, will open an entirely different way of studying black holes, like TON 618. Instead of relying on light, LISA listens to gravitational waves. Ripples in spacetime produced when massive black holes spiral together and merge. This is not indirect inference. It is the universe physically vibrating under extreme gravity. LISA is uniquely sensitive to the millihertz frequency band, where mergers of massive and supermassive black holes occur. These systems evolve slowly, with orbital periods measured in minutes to hours rather than milliseconds. For ultramassive systems, this is exactly the regime where electromagnetic observations struggle. But gravitational waves are strongest and cleanest. One of LISA's greatest strengths is that gravitational wave signals encode mass and spin directly in their waveform. The chirp pattern, how frequency and amplitude change over time, reveals the masses of the merging black holes with high precision. Spin leaves distinct imprints through precession and phase modulation. Unlike quasar mass estimates, these measurements do not depend on gas geometry, orientation, or uncertain scaling relations. For systems that still contain gas, there is the possibility of multi-messenger observations. A merger detected by LISA might be accompanied by electromagnetic signals from disturbed accretion disks or triggered quasar activity. Combining space-time vibrations with light allows astronomers to reconstruct the system in 3 dimensions: mass, spin, environment, and cosmic time, all at once. This matters profoundly for understanding growth histories. If LISA observes frequent mergers involving tens of billions of solar masses, it implies that hierarchical merging plays a major role in building ultramassive black holes. If such mergers are rare, then accretion and early massive seeds must dominate instead. LISA therefore acts as a new ruler, measuring growth not by brightness, but by gravity itself. In this sense, LISA does not just add another dataset, it rewrites how we test black hole evolution. For objects like TON 618, which we only see frozen in ancient light, gravitational waves offer a way to reconstruct their past, their ancestry, and the violent events that shaped them. So if LISA one day detects a truly ultramassive merger, a space-time signal echoing across the universe, what would it reveal about the hidden history behind TON 618? The history of black hole growth is written not in a single object, but across an entire population. When astronomers map quasars across cosmic time, a striking pattern emerges. Quasar activity peaks when the universe was young, roughly at redshift Z, 2 to 3, an era when galaxies were still assembling and cold gas was abundant. This was the age when feeding a black hole was easy, when fuel flowed freely into galactic centers. TON 618 belongs to this violent epoch. It is not an accident or a statistical fluke, but an extreme outcome of conditions that no longer exist today. In that era, mergers were common. Gas fractions were high, and feedback had not yet sterilized galactic environments. If nature was ever going to build something this massive, this was the moment to do it. Compare that past to the present universe. Most supermassive black holes today are quiet. Sagittarius A star at the center of our own galaxy consumes matter at a tiny fraction of its potential rate across nearby galaxies. Black holes are not weak or exhausted. They are starving. The easy fuel is gone, locked into long-lived stars or expelled by earlier quasar winds and jets. This contrast reveals an important truth. Black holes did not fade because gravity became less powerful. They faded because the environment changed. The universe matured. Gas reservoirs thinned. Mergers slowed. The feeding frenzy ended, leaving behind massive remnants that now sleep at galactic centers. Seen this way, TON 618 is a fossil of the quasar era, a preserved extreme, frozen in ancient light. It tells us what black holes could become when the universe was permissive, chaotic, and young. Today, the same physical laws still apply, but the conditions no longer allow such excess. The cosmic banquet is over. The plates are empty, and the largest guests remain where they sat. Dormant giants, surrounded by the leftovers of a long finished feast. So, if we could somehow see TON 618 as it exists right now, not as it was 10 billion years ago, what would we actually find at its core? If we could observe TON 618 as it exists today, the scene would likely be far quieter than the inferno we see in its ancient light. After tens of billions of years of cosmic evolution, the phase of furious accretion that made it a hyperluminous quasar has almost certainly ended. The central engine that once outshone entire galaxies would have dimmed dramatically. Its host galaxy has likely evolved into a massive elliptical system, dominated by old, red stars. Star formation would be minimal, not because the galaxy lacks mass, but because it lacks cold, dense gas. The easy fuel has been used up, locked into long-lived stars, or expelled during earlier quasar-driven winds and jet activity. The black hole itself remains. Gravity does not weaken with age, but without a steady supply of infalling matter, there is no bright accretion disk, no intense ultraviolet or X-ray output, no blazing quasar beacon visible across the universe. The engine is still there, but the lights are off. This is the crucial point. What we observe is not the present state of TON 618. We are witnessing its youth. A brief and violent phase when growth was rapid and visibility was extreme. The silent majority of its existence comes later. Hidden, dark, and observationally modest. In this sense, quasars are self-revealing only during their most destructive moments. They announce their presence by consuming everything within reach. Once that phase is over, they fade into obscurity, indistinguishable from countless other dormant black holes scattered across cosmic history. TON 618, then, is not a permanent lighthouse. It is a cosmic flare. Brilliant, short-lived, and costly. Which leads to the deeper question: why does shining so brightly inevitably sow the seeds of its own extinction? Extreme accretion does not come for free. When a black hole feeds rapidly, its luminosity rises. And with that luminosity comes power in many destructive forms. Intense radiation heat surrounding gas, raising its pressure and making it harder for that gas to cool and fall inward. At the same time, powerful quasar winds driven by radiation pressure can physically expel gas from the central regions at thousands of kilometers per second. As gas is blown out, star formation drops. Fewer new stars means fewer stellar deaths, returning material to the interstellar medium. The reservoir that once fed both stars and the black hole begins to collapse. Jets. If present, add another layer of suppression. By injecting energy into the galactic halo, they prevent hot gas from cooling and flowing back toward the center in so-called cooling flows. The result is a self-regulating system. The very act of rapid growth triggers the mechanisms that shut growth down. The black hole does not simply run out of fuel by chance. It actively destroys its own supply lines. This feedback imposes a natural ceiling on mass, not by forbidding growth, but by making continued growth increasingly difficult. This is why the universe does not fill itself with trillion solar mass black holes. Feedback acts as a governor, harsh but elegant, enforcing balance through violence. In this sense, TON 618 is not a violation of cosmic order. It is the most extreme example of that order operating at its limits. But if feedback is so effective, a deeper puzzle remains. How did TON 618 manage to grow so enormous before this self-strangulation fully took hold? The answer likely lies in timing and environment. Black hole growth is not uniform across cosmic history. There are brief windows when conditions align perfectly. A dense node of the cosmic web funnels gas along dark matter filaments. Galaxy mergers occur frequently, stripping angular momentum and driving gas toward galactic centers. Fuel arrives faster than feedback can expel it. In such regions, a sufficiently large seed or a timely phase of super Eddington accretion can tip the balance. Accretion becomes sustained rather than episodic. Geometry and orientation may further help, allowing radiation to escape preferentially along certain directions, while gas continues to flow inward along others. Growth proceeds not smoothly, but relentlessly. Protocluster environments are prime candidates for this kind of runaway success. They are crowded, gas-rich, and dynamically violent. In these rare settings, feedback may lag behind inflow just long enough for a black hole to leap ahead of its peers. By the time self-regulation finally asserts control, the mass has already reached extreme values. TON 618 appears to be the product of such a sequence. Not a single miracle, but a chain of favorable events stacked in the right order. A cosmic lottery win repeated again and again before the universe closed the door. Yet this raises an uncomfortable possibility. What if objects like TON 618 are not as rare as we think? What if we mostly detect them because they are bright, while countless quieter giants remain hidden beyond our surveys? What we call the biggest black holes, by necessity, the ones that announce themselves, Quasars shine across billions of light years, making them easy targets for surveys. Dormant black holes, no matter how massive, are almost invisible at cosmic distances. Without bright accretion disks or energetic outflows, they leave few observable signatures. This creates a powerful selection effect. Our rankings of the most massive black holes are biased towards systems that are actively feeding. We are not surveying black hole mass directly. We are surveying brightness, variability, and spectral features that only appear during active phases. As a result, the most extreme objects in our catalogues are also the loudest ones. It is entirely possible that even more massive black holes exist in the universe today, hidden inside dust-obscured galaxies or long dormant ellipticals. These objects would not appear as quasars. They would not trigger alerts. They would quietly sit at the centers of galaxies, exerting gravity but emitting little light. This does not invalidate objects like TON 618. Its mass is extraordinary regardless of bias, but it does mean that our current census is incomplete. What we see is only the tip of a distribution shaped by observational limits. To understand the true upper end of black hole mass, we need surveys designed to reduce these biases. Future deep and wide surveys will begin to correct this imbalance by probing fainter, redder, and more variable sources. They will reveal populations that current searches overlook. In astronomy, absence of evidence is rarely evidence of absence. So, which survey is poised to expand the population of extreme quasars and hidden giants the most? The Vera C. Rubin Observatory represents a shift in how we explore the distant universe. Instead of taking static snapshots, it will repeatedly image the entire visible sky over a decade, creating a time-resolved movie of cosmic change. This cadence is crucial for quasar science. Quasars are not steady lights. Their brightness flickers as accretion flows fluctuate and inner disks reorganize. By capturing variability across time, Rubin can identify quasar candidates that might be missed in single-epoch surveys. Extreme luminosity combined with characteristic variability becomes a powerful selection tool. For the most distant and massive quasars, time domain data offers another advantage. Variability timescales place limits on the size of the emitting region. When combined with luminosity and spectral information from follow-up observations, this enables indirect reverberation style constraints for thousands of objects rather than a handful. Rubin will dramatically increase the sample size of known high redshift quasars. With numbers comes statistics. Instead of debating whether TON 618 is unique, astronomers will be able to place it within a population. Outliers will be quantified rather than speculated about. In this way, the future of ultramassive black hole studies shifts from anecdote to demographics. Rare objects become data points. Patterns replace surprises. And the biggest question evolves. When the sample grows large enough, what will we really be asking about black holes at the extreme edge of cosmic possibility, at the extreme end of black hole growth? The central question is no longer how big one object is, but whether there is a fundamental limit at all. One possibility is that the ceiling is imposed by feedback. If radiation, winds, and jets inevitably shut off accretion once a certain scale is reached. Then, the upper mass range is a law of nature. Growth would be self-limiting, regardless of environment or era. A second possibility is that the ceiling is not physical, but temporal. The universe may simply not have had enough time yet. If gas-rich environments and mergers continue far into the future, even larger black holes could eventually form. In this view, TON 618 is not near a hard boundary, but near the current frontier of cosmic history. A third possibility is observational. Our instruments may be blind to the true giants. If the most massive black holes are also the most quiescent, they could evade detection entirely. The apparent ceiling would then be an artifact of how we observe rather than how nature operates. Disentangling these scenarios requires population studies across redshift and environment. If the maximum mass increases with cosmic time, that favors a time-limited explanation. If it remains stable despite changing conditions, feedback likely dominates. If new survey techniques suddenly reveal heavier dormant objects, observational bias is the culprit. This is where astronomy begins to touch philosophy. The question is no longer just what exists, but what could exist. It forces us to confront whether the universe enforces hard limits or merely reveals them slowly. And even if a mass ceiling exists, another question waits beyond it. Once a black hole reaches its final size, how long does it persist into the deep future of the cosmos? Black holes are not perfectly eternal. According to quantum theory, they emit Hawking radiation, a feeble trickle of energy caused by quantum effects near the event horizon. For stellar mass black holes, this evaporation is already unimaginably slow. For ultramassive black holes, it is almost beyond comprehension. The heavier the black hole, the colder it is, and the more slowly it loses mass. For an object with tens of billions of solar masses, the evaporation timescale stretches to roughly 10 to the 100 years, a number so large that it dwarfs every familiar cosmic timescale. By the time such a black hole noticeably shrinks, stars will be gone, galaxies dispersed, and the universe transformed into a dark, thin expanse. In that far future, ultramassive black holes may be among the last complex structures still standing, long after star formation has ceased and protons themselves may have decayed. These giants would quietly persist, marking the end of the stellar era. Their eventual disappearance would be one of the final acts of cosmic history. This perspective reframes black holes not just as destroyers, but as survivors. They are born in violence, grow in chaos, and outlive almost everything else. Their deaths, when they finally arrive, are not dramatic explosions, but slow fades into nothingness. Yet Hawking radiation carries a deeper problem. If black holes evaporate, what happens to the information about everything that ever fell into them? This question leads directly to one of the most profound puzzles in modern physics. At the heart of black hole physics lies a contradiction that refuses to go away. Quantum mechanics insists that information is never destroyed. The exact state of a system can evolve, scramble, and spread, but it cannot vanish. General relativity, on the other hand, seems to say the opposite. Once something crosses the event horizon, it is causally cut off forever, erased from the observable universe. The tension becomes unavoidable when Hawking radiation enters the picture. Hawking showed that black holes slowly evaporate by emitting radiation that appears thermal, random, and featureless. If a black hole forms from matter with detailed structure and then evaporates into radiation that carries no memory of that structure, information seems to be lost. This directly violates the rules of quantum theory. This conflict is known as the black hole information paradox. It is not a technical glitch. It strikes at the foundations of physics. Either quantum mechanics is incomplete, general relativity is incomplete, or our understanding of space-time itself breaks down at the event horizon. Several ideas have been proposed to resolve the paradox. Black hole complementarity suggests that information is both reflected at the horizon and passes through it, depending on the observer. Without contradiction, firewall proposals argue that the horizon itself becomes a violent boundary, destroying infalling information in a way that preserves quantum rules outside. Holographic ideas suggest that information is stored on the horizon surface rather than in the interior. None of these solutions is universally accepted. Each carries deep implications and unresolved problems. What makes objects like TON 618 so important is not that we can test these ideas directly, but that they sharpen the question. Such extreme black holes act as conceptual laboratories, forcing theory to confront its own limits. So, if information is not truly lost, where does it go? Does it remain encoded on the event horizon itself? Or does it somehow leak out, subtly woven into the radiation, escaping to infinity? One of the most radical ideas to emerge from this paradox is the holographic principle. Its core intuition is simple but unsettling. All the information contained within a volume of space may be encoded on its boundary, much like a three-dimensional image stored on a two-dimensional hologram. Applied to black holes, this suggests that everything that falls in is not stored deep inside, but is instead recorded on the event horizon itself. The horizon becomes not a one-way gate, but a kind of cosmic hard drive. As the black hole evolves and evaporates, this information may be released back into the universe through intricate quantum correlations. Entanglement plays a central role in this picture. Hawking radiation may not be truly random. Its subtle correlations spread across vast time scales could carry the information out without violating quantum laws. In this view, the smooth geometry of space-time emerges from patterns of entanglement rather than existing as a fundamental backdrop. This idea sits at the intersection of gravity, quantum field theory, and advanced mathematics. It does not yet offer a complete answer, but it changes the way physicists think about space, time, and reality itself. The universe begins to look less like a stage and more like a computation, where boundaries matter as much as interiors. TON 618, in this sense, is not just a massive object. It is a stress test for our deepest assumptions. The closer we look, the more it suggests that space-time may be an emergent concept, not a primitive one, And if black holes force us to rewrite our understanding of reality at this level, the final question becomes unavoidable. What does that say about our place in a universe that seems to encode its secrets on the very edges of existence? TON 618 is not just a record holder. It is a reminder written in gravity and light that nature is not obligated to match human intuition. When the universe had more fuel, more chaos, and fewer restraints, it built objects that feel almost unreasonable by everyday standards. This quasar is a surviving echo of that violent youth, a time when galaxies were still assembling themselves and black holes grew with terrifying efficiency. It also pushes physics to its edge. TON 618 forces general relativity to perform at extreme limits and asks where quantum gravity must finally take over. It sits precisely at the boundary where our best theories still work. But only barely. And where deeper rules are waiting to be discovered. In that sense, it is not just an object to measure, but a question to live with. Above all, it teaches humility. To understand the universe, we have to accept that we are small, are late, and looking back through ancient light, curiosity without discipline becomes myth. Discipline without curiosity becomes blindness. Real understanding lives in the tension between the two. That balance is the spirit of this channel. Stay curious, but stay critical. If this journey through the depths of TON 618 expanded your sense of scale and wonder, consider subscribing and supporting the channel so we can keep exploring the universe together, one mystery at a time. And now, one last question to leave you with. If the universe has already created TON 618, where do you think the next cosmic monster will appear?